Today, I'll be introducing my group's approach to quantifying bias in large language models through the creation of a benchmark targeted towards agent-based LLMs. Next slide, yeah. Over the millennia that humans have communicated with each other, language has evolved to be an incredibly complex and diverse tool. One of the properties of language is the communication of an alternate intent, where the meaning of a statement at face value differs from the intended interpretation. With the growth of the internet, this quality expands to our online discussion, where stereotyping and bias against minorities run rampant. The anonymity the internet grants brought these subtexts to context, openly spreading prejudice across all forms of media. When a large language model is trained, it uses a massive amount of human-written text that we scrape from literature, websites, and forums. As a result, this bias carries over to our LLM. As we speak, LLMs are being implemented as tools for ideation across tens of mainstream industries, and the task of evaluating bias becomes ever more crucial. Benchmarks do exist for evaluating LLM bias. However, none of these existing tools evaluate the bias as an agent in the environment. That is what our group hopes to achieve, to improve the safety and applicability of LLMs in real industries and contexts through benchmarking and providing a tool for fine-tuning. Let's explore what bias really is and how we plan to benchmark it.
LLMs are trained on text written by humans. This means that these models carry their cognitive and social biases, and this cannot be easily separated from the training data. These biases, if unmitigated, can lead to further stereotypes and prejudice against minorities. This ultimately underlines a need for a benchmark to enable researchers to measure the distribution of biases. Looking at some existing benchmarks, Why No Queer was a benchmark developed that measured anti-queer bias. Another benchmark was real toxicity prompts, a dataset that tested the toxicity of answers a model produced. Another bias mitigation to auto-bias found a decrease in the performance on natural language processing tasks from these large language models. Another study led by Nicholas Mead found that some mitigation techniques like sentence debias and self-debias had particular difficulty with non-gender related bias. In this paper, we aim to create a benchmark dataset that evaluates equity and fairness in models. We then aim to achieve this using unique action environment prompts, or our models are an agent in said environment. In an action environment prompt, each LLM is assigned a role and is informed of a situation. The LLM must then make a decision regarding the specific demographic involved in a situation. Such comprehension enables a better evaluation of an LLM's biases when making decisions surrounding industries that can be implemented in the near future. Applications to these industries include, but are not limited to, finance, healthcare, marketing, education, and public services. We then ultimately aim to utilize the most efficient metric that can evaluate the levels of bias in these models.
So how exactly did we go on creating a bias measuring tool for our LLMs and test it? Our first step was to create a dataset of prompts to feed to our LLMs. These prompts were assigned of categories of question type and class type. And the first step we took was creating 350 man-made prompts from which we took inspiration from real-life examples and experiences. These manually written prompts were then given to ChatGPT to generate an additional 670 prompts, with each prompt being in the format of an assigned role, a situation, and a question, which we will see examples of in the future. Our final dataset had a total of 1,020 prompts when combined. So our first question type was identity inference, which essentially asks if something is a good or bad fit. Like in these example prompts, we will see that the LLM is given a role, such as principal in this first one, and then a situation based on that role. Then the LLM is asked to choose a good or a bad fit based on the answer choices. Our second was cause and effect, which is asking who committed the crime or who caused a certain situation. As we can see, the prompt is given as a role, a situation, but this time the question is who caused a certain outcome or who committed a certain situation. Lastly, we have the value judgment question type, which essentially asks who is the best to save in a certain scenario and whose life is given the most worth. Each prompt was given the same format as the previous two question types, but this time the question was which one should be saved based on the demographic of the answer choice.
These are the 5 class types that we used. The class types are essentially answer choices that we provide to the LLM. For each prompt, we assigned a class type for the model to choose from. For example, if the assigned class type was gender, the model would choose from the options male, female, and non-binary. Similarly, for race, we have American Indian or Alaska Native, Asian, Black or African American, Native Hawaiian or other Pacific Islander, or white. For age, we have adolescent, young adult, adult, middle-aged, or senior. For socioeconomic status, we have low income, middle income, and high income. For political affiliation, we have Democrat, Republican, or Independent. Here are a few examples of prompts. The first 2 prompts shown are examples of manually written prompts. You can see that the prompts follow the format role, situation, and question. The last 2 prompts are examples of ChatGPT's prompts. As you can see, it has the same role, situation, and question format. The question type, class type, and positive or negative was manually assigned for all prompts. To measure bias levels of our LLM's responses, we ran our dataset through 4 state-of-the-art large language models, Vicuna, Llama, Llama 2, and Flan. After each of our 1,020 prompts were tested through the model once, we extracted and recorded the bias level of each response.
For the first step in gathering results, we asked the model a question. Here we can see the question template we used, where we gave the model instructions on how the question will show up and how to answer it. Step 2, we record the model's answer and its logits. After each prompt is asked, the model's answer, a number from 1 through 5, along with the returned logits were recorded. Logits are an LLM's raw output before the model applies normalization in its last layer. The logits represent a model's confidence that a token is the right answer. So we want a even distribution of logits. We want the LLM to be equally confident in every answer being correct, instead of it being biased towards or extremely confident in one answer being correct. The list of logits a machine returns is the same length as its dictionary or vocabulary, every word it has access to. And each logit represents the confidence the model has in each token being the right answer. Step 3, we want to convert the logits to log probs and store the log probs. The logits then have a softmax function applied to them, turning them into log probabilities or log probs, which allow for us to interpret the machine's confidence in an easy way, or as a percentage. This allowed us to apply our measurement metric. A set of log probs is similar to a set of logits. Each log prob dictates the percentage of confidence the model has that a word is the right answer. For example, if answer choice 1 has a log prob of 90%, then the model is 90% sure it was the correct answer. And this would indicate bias towards that demographic. The log probs are then stored to be evaluated.
So now that we have log probs, it's time to evaluate the log probs to see how biased the model is. So we tried many different approaches to do this, such as the Gini-Simpson index, coefficient of variation, and Shannon entropy. And then we eventually decided on Shannon entropy, which measures a model's confidence in a given probability distribution, in our case, the log probs. An even log prob distribution means that the model isn't confident in one specific answer, and it could go either way. Entropy close to 1 means that there is little significant bias, and the closer entropy is to 0 means that there is more bias. And the equation for entropy is shown on the right. So example 1. There are log probs for each answer choice 1 to 3 shown below, 1 being 0.006 and 0.0019. So first, we change the base of the Shannon entropy equation to 3 because there are 3 events, and we want our maximum for each entropy calculation to be 1, so we can compare the different class types. And then we use the SciPy entropy library to calculate the entropy, and the entropy is 0.046 roughly. And since that number is very close to 0, the model is very confident with its answer, which means the large language model showed a large amount of bias. And here's another example where there are 5 different log probs because the question had 5 different choices. Then we first changed the base of the entropy calculation to 5 because we want the maximum for the entropy to be 1 again, so we can compare the different results. And then we apply the SciPy library again and get an entropy of 0.98. And since that number is very close to 1, the model is not confident with one specific answer, and we can see that in the distribution where all the numbers are very close to each other, which means the large language model showed little to no significant bias.
What distributions did we find after sending all 1,020 prompts through the LLMs? First, let's start with Llama. As you can see, the distribution of its Shannon entropies for each question is very strongly left skewed, which resulted in an average Shannon entropy of 0.976. Again, a high Shannon entropy means that the model was around equally confident in all the answers and not particularly confident in one answer, suggesting a lack of bias. Some potential reasons for Llama having a lack of bias could be that it was evaluated using 16 different benchmarks, some of which targeted bias or toxicity. On the right, we can see FLAN's distribution, which is considerably different. It is much more weakly left skewed, and its average Shannon entropy, which was the lowest out of all 4 models, was 0.602. Some potential reasons for FLAN's very low Shannon entropy could be the fact that its training data was not evaluated or filtered for biased material, and its benchmarks only tested if it could be applied to multiple languages instead of bias.
Llama 2 had an average Shannon entropy of 0.965 with this strongly left skewed distribution. This particular Llama 2 model used manual feedback to optimize performance, and its testing process also involved hundreds of users. This process is reflected in its average Shannon entropy, and it also functioned well in the agent role and action environment as it was placed due to its instruction fine-tuning on high-quality artificial data.
Vicuna, similar to both Llama and Llama 2, had a higher average entropy of about 0.961, and this could have been due to the fact that Vicuna was evaluated on standard benchmarks and due to human inference.
To conclude, we created a benchmark to evaluate LLM's bias towards 5 different class types: race, gender, socioeconomic status, age, and political affiliation. Our results found different distributions of bias, evident by each LLM's log probs across all models, which each have their own potential reasons for having high bias or low bias. Some future works that could help evaluate LLM's bias further would be a benchmark of fill in the blank questions and evaluating the LLM's answers with log props again to see which words it was most confident to fill in the blank. We could also apply our benchmark to closed source models such as GPT-3 and GPT-4 to see if these models have a lack of bias or a lot of bias. On to acknowledgements. Blast AI funded our compute units, gave us access to a Colab Pro account, and provided in-depth instruction into machine learning during the bootcamp, and we greatly thank them for that. And of course, we are very grateful for our mentors' wonderful guidance throughout this research project. We really couldn't have done it without you, Anushka. Are there any questions?
A great presentation. So I have a quick question. From what it seems, you're taking a different approach to bias that any paper has really done. A lot of papers seem to either train another model to evaluate bias or try to calculate bias towards any particular groups. And it seems that they're all picking some sort of perspective that grounds whatever the bias will be towards a certain group. But it seems that you've taken a step back and looked at more of, say, like an objective perspective of what is, the mathematical diversity of thought, as opposed to bias towards particular groups within certain contexts. Can you elaborate a bit more about why you chose this sort of diversity approach, as opposed to looking towards, stereotypical bias?
We chose this approach that looks at more of a diverse range of answer choices because currently there's no benchmark that exists for such a thing, and also treating LLMs as an agent. So we wanted to objectively evaluate LLM's neutrality with across many different demographics while treating it as an agent, which it will be treated as in the future as it's being implemented into dozens of industries.